just have to go now. I'm really sorry.
That's okay.
I'll
See you.
I'll come to the next one.
Okay, so again, if everyone hasn't seen it, please answer the question that is at the link in general chat. There's currently no answers.
Are you streaming it, or did you have to switch your output?
Uh, Maybe I didn't share this correct screen from the beginning. Hang on.
Yep, there we go. Alright.
There's not supposed to be a picture or anything, right? It's just the
Nope.
conceptual.
Yep, just conceptual. Is it fading in and out now? Yes, it is. Okay. All right, we'll just give a minute left. Let me see if I can fix the bar thing real quick.
I'll now look at random quotes and bots. I sniped a message.
Okay, well, last person here isn't answering, but we'll just go ahead and move on. Nice. Okay, so remember what we just talked about momentum is conserved, right? It says that there are two objects or cars in this case that are of equal mass, which is irrelevant to the question, but it just mentions that, and that they're moving on a linear and frictionless track. So there's no other forces acting on the system, and when there's no other forces acting on the system besides the forces of the collision, then the momentum is conserved. Momentum is always conserved when there are no external forces on a system. You have to remember that because that's one of the biggest hidden variables when dealing with momentum problems. If you forget that momentum is conserved, the problem will become pretty much unsolvable. Are there any questions?
So in the example of the box and ball,
Mhm.
the ball had an initial momentum of what was the initial momentum of that?
It
Or
was
is
10.
that even okay? Oh, okay, I see.
So
Never mind.
since the ball had no momentum at the end, has zero momentum, the momentum of the box had to be 10 because the momentum was conserved.
Okay.
Okay. So, okay, so for the next part, let's go back to the equation we had before um, with force and momentum, which was F net is equal to change in momentum over change in time. So we can use this as well to figure out things like how much force it takes for an object to stop in a collision, right? So um, let's say we have a wall over here, and we have a ball that is 2 kilograms, and it's traveling towards the wall at 5 meters per second. And then when it hits the ball, the ball, compresses, and it takes 0.04 seconds for the ball to come to a complete stop. So how would we figure out how much force is required to bring the ball to a stop in that time? Using momentum specifically.
So the weight is 2, the velocity is 5. That's the time. Okay, so
So like we set up here, in order to get FNet, we need to know a change in momentum and a change in time. And we already know the change in time. It's 0.04 seconds, right? So how can we get the change in momentum?
multiply by net force.
Well, we don't know net force, though. That's what we're trying to find.
Oh.
We're trying to figure out how much force does it take to stop the ball when it hits the wall in 0.04 seconds.
Oh, you multiply the mass times the velocity, so it'll be 10 over 0.04.
Yes. So I'm just going to explain specifically why that's the change in momentum, though, because at the beginning, its initial momentum, is its mass, which is 2, times its velocity, which is 5, which is 10. And what is its momentum at the end when it's completely stopped?
0.
Yep. So if its initial momentum is 10 and its final momentum is 0, then change in momentum is going to be negative 10.
What are you're referring to, the ball or the box?
The ball. The ball. This
Okay.
this is a wall in this example. Not that it really
Okay.
matters, but all we need to know, we don't know anything about the wall here, just that it stops the ball completely, right? And so the initial momentum of the ball was 10, and the final momentum of the ball was 0 because it said it came to a complete stop. So the final momentum of the ball, the change of momentum of the ball is negative 10. So we can say that the net force on the ball for the entire duration had to be negative 10 over the amount of time, which is 0.04 seconds. And that would say that or I didn't divide it there. All right, so that means it took 250 newtons of force in that direction, in the left direction, the negative x direction, to stop the ball in 0.04 seconds.
All right.
Are there any questions about this one? So we talked about conservation. We talked about how we can compare it to force. So the next thing is elastic versus inelastic collisions. Do you know what the difference between an elastic and an inelastic collision is?
I don't, but I just had a small confusion on. I know it's the earlier problem, but I was just thinking, the ball and the box. What I was confused about is, um, the initial momentum of the ball was 10, and the box was at rest, so that initial was 0. Why did it? Because of the collision, the final momentum of the box became 10.
Right, because I told you as part of the problem that
Momentum's conserved.
well, that you need to know, but I told you specifically that after the collision, the ball was not moving. So the final collision or the final momentum of the ball was 0. And so since I also said that there was no other forces acting on anything except for the forces of the collision, then momentum is conserved because momentum is always conserved when there are no external forces.
Okay. All right. And then no, I don't remember what the elastic thing was.
Okay. So in an elastic collision, energy is conserved. So for example, what we could say is we have two objects. Oops. let's say we have two objects here and here. And the initial, or so the mass of this one is going to be 0.5 kilograms. And the mass of this one, I'm going to just write 1 and 2 over here. And the mass of this one is going to be 3.5 kilograms. And this mass over here is moving this way at 4 meters per second. And this one over here is not moving, actually. We'll say this one over here is moving at 0 meters per second. So we want to know the velocities before and after the collision. Or well, we already know the velocities before the collision, so we want to know the velocities after the collision. So and we're going to say that this problem is elastic, right? So we're going to say that energy is conserved. So if we know that what is the initial energy of this box here that's moving at, or conditional kinetic energy of this box that's moving at 0 meters per second?
0.
Yep. And so how can we find the initial kinetic energy of the first box over here?
1/2 mv squared.
Yep. So 1/2 mv squared, and that's going to be 1/2
This can be
0,
yeah,
0.5
be 1. Oh wait, no, that's not. That's wrong.
4 squared, and let me just work it
Ooh.
out just to make sure. It should be 4. Is that what you got as well?
1 sec. Oh, what I do? Yep, got 4.
Okay.
That's also what I got.
Yep. So then the other piece is that, remember, that momentum is also conserved. So again, what is the initial momentum of the system? So that's going to be energy naught. And then momentum naught. What is the initial momentum of the system? So let's just start with this box because it's easiest. What is the initial momentum of this box?
The 0.
Yep. And then what is the initial momentum of this box?
It is 2.
Yep, the initial momentum of this box is 2. And Alan, I forget, what are the units of momentum again? Is Alan there?
Yeah, what's up?
Yeah, what is the units of momentum again? I forget.
Oh God, I don't remember at all. Is it? I thought it was like
kg times.
it's
m
like some
over s.
weird unit. Like it's not. I don't remember. Hold on. I thought
says
it was
I
like
think
the.
kg m over s. That's what
It's just kilogram meters per second. That's all it is.
Yeah,
Yep.
There's no like actual name for it. It's just kilogram meters per second. Sorry, I was eating food.
Okay, that's fine. Okay, so we know the initial kinetic energy and we know the initial momentum from all of this. So remember, we're looking for the velocities of the ending two objects, right? And since the very beginning, the second object, it had a momentum of 0, we can say that the final momentum of the first one plus the final momentum of the second one is equal to the initial momentum, which I'm just going to replace with 2. right? So whatever these two are moving at the end, their momentums has to be 2. And we're going to substitute that with the equations here. So the mass of the first one was 0.5, and then times v1. And the other one was, I believe, 3.5. Yes.
Why would
Was
we not know V1?
we don't know the final velocity after the collision. V1 in this case is referring to the final velocity.
Oh, okay.
So 3.5 times v2, which again refers to the final velocity. And so the second part of this is that we can say the initial kinetic energy is equal to the 1/2 mass of first mass times its final velocity squared plus so this is basically saying that the initial energy is equal to the final energy of both of them. V2 squared. And then obviously we're going to go ahead and replace these with 0.5 v1 squared and 3.5 v2 squared. Okay, I know that momentum problems are confusing, and that's just how momentum problems are. Are there any questions so far? I want to make sure I haven't lost anyone,
So
or the 2 people we have.
why are you doing this? To solve for what?
We're solving for the final velocities of both of the objects.
And that's just a formula. P1 V1 plus.
So it's not
V1.
a
Oh my.
static formula. You have to understand that, and I know there's too many letters, and it's kind of difficult. But what you have to understand is that you can get an initial momentum and an initial kinetic energy, and you can get a final momentum and a final kinetic energy. And the initial momentum is equal to the final momentum, and the initial kinetic energy is equal to the final kinetic energy. Those are the 2 pieces you need to know. And the only reason you know about kinetic energy in this one is because it was said that it's completely elastic, or that any elastic collision, energy is conserved. So energy is the same before and after.
Okay.
It's
Sorry, I was
it's
mixing.
more like energy, where it's not an equation you use. It's just saying I have x here and x there, and I can set them equal to each other.
Okay. Yeah, I was mixing some random Boyle's law into this. I don't know why. P1, I saw P and V, so my bad.
Yeah. So now what we're going to do is we're going to solve one of these equations for one of the velocities. So I'm just going to pick this one because it's easier, but it doesn't matter which order you do this in, you'll get the same answer. So rearranging that, we should get 0.5, the final velocity of the first object, is equal to 2 minus 3.5 times the velocity of the second one. Divide everything by 0.5. So the final velocity of the first one is equal to 1 minus 3.5. Oh wait, it's divided by 0.5. Never mind, this is 4. Minus 3.5 over 0.5, which is just 7, v2. And so now that we know this, we can then substitute into the, so this at this point is pretty much just solving systems of equations, right? We can then substitute this v1 into the kinetic energy equation for v1. So that becomes, and remember, I'm going to also substitute, I'm going to substitute this E naught, which is the initial energy for what we said over here, which is 4. So now we can say 4, move back up. Okay, so 4 is equal to 1/2. I need to see what that was. 1/2 times 0.5 times 4 minus 7 v velocity second squared plus 1/2 3.5 velocity second object squared. And so now we only have one variable in here, right? We know everything else. So we can solve for the velocity of the second object squared, and that should just be algebra. And then once you find the velocity of the second object squared, or just you can find the velocity of the second object from this equation, then you know the velocity of the second object, and then you can plug the velocity of the second object into this equation, and then solve for the velocity of the first object. And then that's how you would get the velocity of both of them. Do you need to see me? The rest of that's just algebra. So does anyone need to see me solve that fully out, or do you understand what you would do?
If you could, that would be good.
Okay. So this is going to simplify to 4 times, or 4 is equal to 0.25 times 4 minus 7 v squared. So I have to do FOIL. 4 minus 7v2. I have to draw a FOIL. I can't do FOIL in my head. Okay, so that is 16 minus 14 v2 plus v2 squared. And then over here is 1/2 times 3.5. Which is 1.75. And then that's v2 squared. We can combine these two terms to get 2.75 v2 squared. And I will add back the 4 equals at the beginning. And then that ends up, we can combine the rest of these terms. So 0.25 and 16 combines to 16.25. And then we're left with minus 14 v2 at the end. Those two middle terms should really be swapped. But then now you're left with this, and we can subtract 4 from both sides. So we can end up with 0 is equal to 2.75 v2 squared minus 14 v2 plus 12. I have to move it again. 12.25. And then you can either use quadratic equation or just plug it into your calculator to get the v2 using the polysimults on your calculator.
Okay.
So just for the sake of completion, what is it? 2.75 negative 14 12.25. And then that is v2 is equal to 1.122 meters per second. And then, like we said before, you plug v2 into the momentum equation, which is up here somewhere in the mess of equations. Yeah, right here. So you're going to plug that value of v2 in right here. And then you're going to solve for v1 over here, just using algebra. Do you need to see me do that part, or does that make sense?
No, yeah, that makes sense. That makes sense.
Okay. So again, momentum problems are annoying and a lot of times confusing, which, I mean, rip for the people not here. I guess. But momentum does take some time to sink in, especially because momentum problems tend to be a lot of this systems of equations, which just ends up getting annoying. But do you have any questions so far?
Um. I was just like, I'm so slightly confused on the like um how you got from, like, could you just walk through, like, I get all the algebra stuff, so there's no need to go over that, but like how you got from the beginning of the problem to the equation,
Right.
like,
So
yeah, like how what made you use that set of.
right. So if we were so when I said the problem, I said a couple things, right? I said we have two objects that are of some masses, m1 and m2 in this case, right? Doesn't matter what they are, and that one has some velocity, and then the other one is not moving, right? And then I said two other things. I said that there's no other forces acting on the system, so there's no friction or anything like that. And that whenever you hear that there's no forces acting on a system, or it implicitly tells you that by saying there's no friction or air resistance or anything like that, then you know that momentum is conserved, or that change in momentum is equal to 0. And the second thing I said was that the collision was an elastic collision. So that also means that change in energy is equal to
It
0.
was in elastic, or was
Elastic.
n.
And
Okay, okay,
N like AN, elastic.
okay, okay,
Yep. So when it's elastic, energy is conserved, so change in energy is equal to 0. So
okay.
the thing that you have to know whenever you're doing problems, right? If it asks you to find one value and you know, because really in any collision, there's 4 values total, right? There's initial mass of the one object, initial mass of the second object, final mass of the, or there's, I guess, 6, final, or 8 total, sorry. So there's initial mass of the first object, initial mass of the second object, and for initial velocity of the first object, initial velocity of the second object, final mass of the first object, final mass of the second object, final velocity of the first object, final velocity of the second object. Most of the time, um, the masses are the same. So you just, the initial mass of one object is equal to the final mass of the other object. So you have to, that doesn't matter. But when you're given, so then out of the remaining 4 velocity variables, if you're given 3 of them, right, you're given the 2 initial and 1 of the final, for example, then you can just use momentum. All you need to know is that momentum is conserved. But in this example, we were given 2 of the velocities, the initial velocity, and it was the question asked us to get the final 2 velocities. And the only way to get the final 2 velocities is to combine 2 equations. You cannot get 2 velocities just from momentum. So they have to give you something else, which in this case was that the collision was elastic, which allows you to use change in energy is equal to 0, and that's your second equation. Sorry if I kind of explained that in a roundabout way, but
Change in energy is equal to 0. Yeah, that's correct. Yeah, because of, okay, elastic.
yeah.
Right.
Because like just think about algebra for a second. If you know x is equal to like 1, right? You can, and it doesn't have to be 1, but anything over on that side, you can solve for x, right? But if I said x is equal to 2y, there's no possible way to solve this. You cannot solve this equation by itself. You need a second
Yes.
equation. When you have
Yeah.
one equation, or when you have one variable, you only need one equation. When you have 2 variables, you need 2 equations. When you have 3 variables, you need 3 equations, and so on. So in this case, we needed to find 2 different variables, and we were only given the first 2, so we had to use 2 different equations. Whereas the first examples I gave you 3 out of the 4 variables. There was only 1 variable missing, so we only needed to use momentum.
Correct.
Does that make sense?
Yep.
Okay. There's not a whole lot I can go into after. Alan, do you have any comments?
Well, there's another one, which is that momentum. If you're still trying to understand this, like, kind of intuitively, I guess, like or it's still not making sense. Momentum is like you can't really measure momentum. Is the thing. Like it's not tangible like uh other quantities that we can measure. And that's because it's basically just a way to calculate collisions. Like that's what it's made for. So, and correct me if I'm wrong, Nathan, but that's the only time you use momentum, right? It's just for collisions.
Pretty much, yeah.
Yeah. So,
I mean, the only other case is like rockets, right? Because rockets throw out mass in order to go. So
Right.
any the other cases in when there's changing mass is the other case when you can use momentum, but most of the
Right.
time it's just collisions.
yeah, but it's like it's it's only going to be used for those for a couple of scenarios, and for those it should be pretty obvious because they'll give you a mass and a velocity, and you can't solve it with energy. And then that's basically just a momentum problem.
Okay, so like I said, momentum is just overall annoying, but it ends up always just being systems of equations. So if you're good at systems of equations, this is not that bad. But it is tends to be very confusing as to when to use what. Um, so sort of because of that, next meeting will probably be a lot of practice problems because the thing that well, we're going to go over inelastic as well. But then after that will be practice problems because we just have to get good at identifying when to use which equations to combine to get the final answer. And that's pretty much all there is to momentum.
Okay.
Okay. That's pretty much it for today because we only have 5 minutes left and I don't want to get into the next part because that's going to take too long. So,
All right.
yeah.
Thank you. See
All
ya.
right. See ya.